Hi friends, welcome to our channel. In the previous session, we had discussed the concept of phases of compiler with some example code segment. In this session also, we will move to the same concept with another example. Consider a source program int I comma j. So two variables declared as integer and I is equal to I into 50 plus j plus 3. Assume this is the source program. Now, this source program is passed to all the 6 phases of the compiler, and what is the final output? That is our target. What are the 6 phases of the compiler? First one is lexical analyzer, second syntax analyzer, third semantic analyzer, fourth one is intermediate code generator, fifth one code optimizer, and finally sixth one is code generator. Now we will discuss each and every phase. What is the input? What is the output? This is the source program, this one. Now this source program is passed as input to the lexical analyzer. So now what this lexical analyzer do? Simply lexical analyzer reads the source program character by character and then generates tokens. Reads character by character and then generate tokens. What do you mean by token? Token is simply anything of the source program. That means either a variable, constant, operator, identifier, whatever it is. Each and everything is called token. The tokens are generated from the lexical analyzer. Now how it is generated? Like this. I is the variable. The token I is an identifier. So identifier is equal to operator is as is I. Already I is occurred. So ID1 into 50 is a constant. The constants of variables are written like this plus J is an identifier. ID1 is already completed. Use another identifier plus 3. This is a tokenized output generated by lexical analyzer. Now the lexical analyzer also maintains symbol table. What do you mean by symbol table? Simply the complete information about the tokens. Complete information about the tokens is maintained by the symbol table. For example, 1, 2, ID1, ID2 and so on. Here 1 comma 2 are attribute values. These are used, that is these attribute values acts as a pointer. That means these are used to access the corresponding information about the identifier. Here not only name of the identifier, we have the value of identifier, we have the scope of identifier, the remaining different parameters for a particular identifier are maintained by symbol table. Now, that is not our thing. Now, our thing is this tokenized information is passed as input to the second phase syntax analyzer. What this syntax analyzer do? The syntax analyzer simply construct a parse tree. Syntax analyzer simply construct a parse tree. Now I will construct the parse tree. How the parse tree is constructed? In the parse tree, remember the internal nodes acts as the operators. The remaining are called left and right child. Each and every operator has some priority also. So the operation is done level by level. Observe is equal to multiplication, addition and addition. So highest priority is for multiplication. And you have a doubt, both plus and plus have the same priority. In case if more than one, that is if an operators with the same precedence appears in an expression, then you have to consider the associativity. The The operator plus is from left to right. So what happens? First this expression is evaluated, right? So into ID1 50, right? This is completed. Now for this expression ID2 is added, already completed. For this one ID2 is added, so plus left side is this one, right side is ID2. Now this entire thing is completed. Now for this expression 3 is added, so up to now this is this part. For this one plus left side is this one, 3 is added. Now the entire expression is assigned to ID1 by u is equal to operator ID1. So this is the parse tree. This is the parse tree. Now this parse tree is passed as input to the, now I am erasing this one, the outputs of two phases, lexical phase and then syntax phase. Now this parse tree is produced as input to the semantic analyzer. Semantic analyzer. Okay, this semantic analyzer produces correct parse tree. Correct parse tree. What do you mean by correct parse tree? Another name is called either modifier parse tree or annotated parse tree For example, see the source program. In this I comma j are declared as integer variable. For example, our expression is like this. ID1 is equal to ID1 into 50 plus ID2 plus 3. Assume if this is a floating value, float into an integer, the answer is float. Float plus integer, the answer is float. That means what happens? This 50 is automatically converted into 50.0. 3 is to be converted into 3.0. You have to perform type conversion. Simply, the semantic analyzer perform all such type conversions and generate the annotated parse tree. See this one? So, the remaining other than constants, the remaining are same. Plus ID2 for this star, the left side is ID1, move to right side. Here and here we have constants. Simply 3 is converted into 3.0. For that we are writing like this, into 2 float 3. So into 2 float operation is performed for the constant 3. Similarly, into 2 float operation is performed for the constant 50. This is the output of semantic analyzer. This is called correct parse tree or annotated parse tree. Now, this output is produced input to the intermediate code generator. Intermediate code generator, that is the fourth phase. Code generator. Intermediate code generator takes the output of the semantic. What it produces? The intermediate code generator produces an intermediate code in 3 address format. In 3 address format. Okay, 3 address format in the sense it can use a maximum of 3 operators. And if you want to generate the intermediate code in 3 address format, you have to remember some rule. One simple rule is the compiler automatically generates temporary variables to store the result. So here we have some set of variables. Along this variable, the compiler can create temporary variables for storing the result. So the first one is temporary variables. One more thing is, suppose an expression contains, generally we think that 3 address in the sense the maximum of 3 operators. Not only this one, it can contains less than 3 operators, it is also allowed. If an intermediate code contains less than 3 operators, that is also allowed. And one more thing is, if an expression contains assignment operation, the right hand side contains a maximum of one operator. This is the most important thing. If an expression contains assignment operator, the right side of the assignment operator can contains a maximum of one operator is allowed. That is, it can use either 0 operator or 1 operator. Other than 1, it is not allowed. Now, for this annotated pository or correct pository, we are generating the intermediate code by using 3 address. Now see, step by step. Generally, we are moving from down to top. What is the first step? 50 is to be converted from integer to float. Assume a temporary variable t1 which stores into to float of 50. So t1 stores the value. This thing is completed. Now this is stored in t1. t1 stores the value into 250. Now perform multiplication operation. Now you have to perform multiplication operation. Multiplication operation in the sense id1 is equal to id1 into this one, or here you can use the temporary variable simply to store the result. t2 is equal to id1 into t1. That is, this entire thing is completed, right? This result is stored in T2. Now, perform addition with ID2. Suppose T3 is equal to T2 plus ID2. T2 plus ID2. So, this entire thing is completed. Now, this result is stored in T3. Now, before performing addition, you have to perform this operation. So, T4 is equal to into 2 float of 3. So this thing is T4. This thing is T4. Now perform addition operation between T3, this result, and T4, this result. So T5 is equal to T3 plus T4. Now this entire thing is completed. Step by step you have to follow, level by level, level by level. Finally the last thing is stored in id1. id1 is equal to t5. Now observe what are the three rules. It creates some temporary variables t1, t2, t3, t4, t5. It is allowed. If you have an assignment operator, the right side is the maximum 1. Maximum 1 in the sense minimum 0. In this case, 0 operator is placed. Now, an expression contains less than 3 operators is also allowed. Here only 1 operator. Everything is possible. These are the rules we have to follow for generating an intermediate code. Okay. So, how many number of instructions? 1, 2, 3, 4, 5, 6. A total of 7 instructions are produced. Now, this intermediate code is passed as input to the code optimizer. The name specified. This is the fifth phase. The code optimizer. What do you mean by code optimizer? It optimizes the code. Optimizes the code in the sense removing unnecessary instructions from this code. Removing unnecessary instructions from this code. What do you mean by this one? Suppose first you are performing this operation and this result is stored in T1. Instead, and T1 is multiplied here. Instead of that, directly write this statement here. That one line is reduced. T1 is equal to ID1 into 2 float of 50. Now observe, these two statements are combined together as a single statement. Combined together as a single statement. Suppose T2 is equal to, observe these names and these names are different. Here I am using another set of temporary variables. T2 is equal to whatever the result. What is my expression? Remember your expression. Here I am writing ID1 is equal to ID1 into 50 plus ID2 plus 3. So this thing is completed. 50 is converted into integer, multiplied with ID1, that is placed in T2. Now we have to add with ID2. T2 is equal to this result, T1 plus ID2. Similarly, this is completed. These two are merged together. T3 is equal to this one. What is this one? This result. T2 plus, simply observe, T3 value is this one. What is this one? Exactly, this is the one. Simply I am reducing the code. T2 plus into 2 float of 3. So T3 value here is T2 plus I2. Here is this simply T2. T4 value is into 2 float. Here also into 2 float. Finally, ID1 is equal to T3. Observe, the number of instructions are reduced. Instead of writing multiple number of instructions, we are reducing the number of instructions. Finally, this output, that is the optimized code, is passed as input to the code generator. So simply, this code generator phase loads the instructions into the memory for execution. Okay, so move to code generator. In this code generator, we are using two types of instructions. One is load, another one is store. This is one set of instruction, or some another category is directly move. So load is one instruction, store is another instruction. This is one pair. So accumulator comma memory. Simply load means transfer the information from memory into accumulator. This is performed by using load operation. Transfer the information from accumulator into the memory. Accumulator into the memory in the sense, for execution we are storing into the memory. This is the store instruction. Here for code generator we are using these two instructions, or simply you can use a single instruction move. Actually in the previous example we discussed with move. That is the reason in this session, in this example, we will discuss these two. Okay. So whatever it is, you can use this pair or this one. Everything is possible. Actually, load is represented as LD, store is represented as ST, and along with we are using LDF. F is the sense it is used to store floating point numbers. F is used to store floating point numbers. Now, write down simply R1 comma ID1. This is my first step. R1 comma ID1. Actually, my instruction is ID1 is equal to ID1 into 50 plus ID2 plus 3. ID1 is stored into register R1. ID1 is stored into register R1. Now, you have to perform multiplication operation. Perform multiplication operation. So, multiplication F of. So, actually your ID1, this is placed, remember, in code generator, instead of this one, you have to use registers only. That is the reason. First I am passing this ID1 into R1 and then perform this multiplication. ID1 is present in register R1 multiplied with 50. So hash 50.0. Why 50.0? If you are performing this operation, automatically 50 is converted into 50.0. And before a constant we are using hash symbol. Now perform multiplication between these two and again stores the result in this one. This is this way. The right side is the source, left side is the destination. Perform multiplication and result is stored in R1, right? This multiplication is completed. Now what to do? you have to store ID2 in some other register, right? You have to store ID2. Directly the variables is not at all performed. R2 comma ID2. So this operation is completed. That is this thing. ID2 is placed in register R2. Now perform addition between T1. T1 is this one. This entire result is in R1, right? So same thing. Addition. F says floating point number. R1 comma R2. R1 in the sense this entire thing is R1. This is R2. Perform addition between R1 and R2. Again the result is copied into R1. Now this entire result, this is also right now R1. Right now this is also R1. Now again perform addition operation. Again perform addition operation. Right? So this T2 is R1. R1. This into 2 float is written like this, hash of 3.0. Perform addition and that is assigned to some register. Again use the register R1, not a problem. Add F. Finally the value, whatever the value in R1, that is stored in ID1. Now here you have to perform store operation ID1 comma R1. Observe, if it is a variable on the right hand side, you have to use the register for storing the variable. After performing all the operations assigned to ID1. Remember, whenever you require the old register, create a new register. If you are not requiring old register, and each and every time, suppose here R1 stores ID1. Here, this entire thing is stored in ID1. Why? Because now old ID1 is not at all required. Here also old R1 is not at all required. If you required, you can create another register. If you are not required, simply use that particular register. This is the output of the code generator. So these are the different phases of the compiler. Thank you.